Hello everyone, my name is Nicholas Ray, and I'll be starting off for Group 6 Project Trace presentation. My role in the project was to do the initial topic modeling and also work on the web scraper and import things into the database. So at the very beginning here, I went to the NSF federally funded award website and took all the CSV files corresponding to the awards that the professor specified, and then did some topic modeling based off of the titles and abstracts. These are the libraries I use. The standouts here are GenSim and NLTK, being very natural language focused and very specifically LDA focused with GenSim. Here is an example of one of the CSV files that I've gotten from the website. We've narrowed it down here. There's many more fields that come in the CSVs, but we're only working with the award number, the title, and the abstract here. As you can see, they're just some paragraphs of text, and we're going to tokenize them and work on them like we did in the assignment. And like we're saying here, we're just taking title and turning everything in there into a NumPy series, which is just the kind of paragraph and its index. We do the same thing for the abstracts. And as we have tokenized those NumPy series, we import them back into the data frame. And we can see here that the paragraphs have been segmented up into words and as just a list full of all the terms. And on the right side, you can see, at least for a titles example, the frequency of the terms in all of those titles and that are titles, yes. Working with the words, we had to remove quite a lot of stuff. I used the stop words filtering from NLTK library, and you can see that just removes things like the, I, you, a, with, not important terms, only leaving the main subjects left behind. As we see here, all the terms have been kind of visualized in a word cloud, and their frequency correlates to the size of the word. And this is just one representation of the CI/CI CSV file. Getting the data ready for the LDA modeling requires the data to be vectorized, and we can see a visual representation of that here. And a more specific representation here where we take a Python list full of just some terms and vectorize it into a kind of list of tuples. The initial number of the tuple refers to the actual word, and the second refers to the frequency in the list. For this example, obviously, they're all 1. Once that's all ready, we can actually create our model and then get some results. As we can see here, I use the GenSim library to call the model's LDA model and just populated one for the titles and one for the abstracts, and used about 10 topics as a general number to go by. After we've done all that clustering, we have a bunch of clusters of words, and we combine them into a keyword set, meaning there's no duplicate terms, so we don't have any problems of getting the same queries over again, and we just output that to a text file. The web scraper uses that text file in the upcoming things to query all the websites based off of the keywords and put them into a file format that our database can use. These are the libraries I use for the web scraper, Beautiful Soup and Google Search being the two main ones, while Mongo import, JSON, and datetime are used for importing things into the database, as well as a kind of file path and directory kind of manipulation. This is just a bird's eye view of the scraper. We take the keywords text file, we give it to the scraper, and we get JSON files from the scraping. The text file is kind of divided into its kind of actual file path award term, and then we go through every line in the file and use that as the keyword and loop through all of them, pulling queries from Google, and then using Beautiful Soup to pull that HTML and parse it. Here we can see the Beautiful Soup library parsing the HTML text into a JSON dictionary, which is just used to import it into a JSON file. You can see here that we're pulling some things from the soup and kind of using that as the values of our dictionary. We take that JSON dictionary and use the JSON library to dump it into a JSON object, which can be easily written out to a JSON file. The JSON file is then used with the bash shell that we are hosting our database on. We move it over to the shell, and then we import it into the database. Some of the challenges I fell into, mainly on topic modeling, were data cleaning and tokenization. this wasn't very much problems. It was just kind of little fiddly things, removing single character words and other stuff that was just kind of junk, and then preparing that for the model itself. On the web scraping side, I had much more obstacles and challenges. HTML is messy, and I learned that I kind of did a lot of inefficient things at first and kind of streamlined the process later. And working in the shell itself was also kind of difficult. Here we can see kind of just a simple visual representation of how HTML on the left looks ugly, and it only looks nice when CSS formatting is added to it. Also, talking about those inefficiencies, at first I had the web scraper just saving the raw HTML files, and I had a converter that we converted things to JSON with. But this was very redundant, and eventually I realized that I should have been saving things as JSON files and not kind of adding this extra step. While moving on to the actual importation into the database, working on the shell wasn't that hard. My experience on the Fox servers definitely supported me here. But working with Mongo import, I found a lot of interesting documentation as well as bugs and things that maybe if the JSON file was too huge, it would just like fail the import and a couple of other things. What we see here is just an example of a command line prompt where we cat all the JSON files in a directory we're currently working in, and we import them into a Mongo collection that we can specify by name. This is just an example command. There's many arguments and other things that you can add to this, such as the database you're working with, or special commands like if you want to drop something completely before populating it again to avoid that kind of doubling up on data. So now that we've finished with the presentation, I'm going to go ahead and give you guys a look at the web scraper in action. So as we see here, the web scraper on the kind of just terminal below, it's just outputting every link that we're working on. And if there is a problem with that link, depending on the try and catch blocks that I've set up in the code. As we head up to the code here, we can see that after our imports, the first thing we do is work with a specific keyword file, and we also then kind of parse that file for the file path that we'll be working, the directory we're going to make, and also the kind of name of every file that's going to continue on. Once we have those, we initialize a URL set and a URL list just so we can kind of work in a tandem to avoid duplications if Google sends us the same link. And as we can see here, as we enter the for loop, for all the keywords in the list, this instance we're trimming a little bit from the front because I had to stop this instance and check something. But we take the keyword in the keywords list, we create a query, we print it for verification, we search that query with the Google search call, we kind of filter the query to make sure we don't have any PDFs in there. So we add the URL to this list and avoid the PDFs links that kind of give us some trouble, or at least I had some trouble with them. We get the date, time, and the current working directory. We try to make a new directory if it doesn't exist to kind of populate all our files in. We clear the set just in case it's got something in it. And then we use that set and the URL list to make sure that we're not doubling up, like I said before. We take the keyword, we create a query. We then kind of send that query to the request call, and we get a HTML back. That HTML is parsed by Beautiful Soup. And then eventually we just output it to a file, and you can see that that's really all we're doing here. All right, so as we move on to the next member of the project, I'll hand you off now.
Alrighty, my name is Jeff Dong, and now I'm going to be going over my portion of the project that I was focusing on, which is in regards to actual cleaning of the database and transforming all of the data that we're getting into valuable insights and different analyses so that we can then display them on the website. So, like Nicholas was talking about, we're collecting all this data and we're scraping a whole bunch of different pages from the web. How do we then take all this data just sitting around and transform it into something that we can actually use? So first off, let's talk about the actual cleaning itself. Now, the only libraries I needed to use was PyMongo itself in order to connect to the database, write it, and do different cleaning on the different topics and different collections inside the database itself. So one of the first things I needed to clean and identify was different errors in the pages themselves. So most notably, we have these generic 404 not found errors from web pages. Due to the nature of web scraping itself, we're going to be run into a whole bunch of different pages and different data that we just can't use. So it may not be these 404 errors, it can be 403 forbiddens, or it can be different under maintenance warnings, or etc. etc. Basically, we try to query a page, we scrape it, but unfortunately, the page didn't load for whatever reason. But that's not the only thing we're going to be worried about. We're also need to worry about is if the pages that we're collecting are too small. So as you can see in this example right here, there's no explicit error in this web page. There's no, hey, you can't be here, or I'm sorry, this page didn't load. Instead, this web page was just the name of the website itself. So just like the assignment when we were doing topic modeling on tweets, we need to realize that, okay, if this if any single document is too small, then we more than likely can't generate any meaningful analysis on it. So in addition to these more generic errors, we're also going to need to clean and wipe out these small documents as well. So just showing some examples in one of the smaller collections that we're using, but over 7,500 of the web pages in there were simply empty, not even an error, just nothing loaded. But in addition to that, just showing an example of something where the web page wasn't able to give us any meaningful information. So we can see here, I was looking for any page that had an access denied into it. So there's no server-side error. The page did load, it's just that we couldn't access any meaningful data from that page. So after all that cleaning was said and done, these are all the stats on each of the different collections that we're able to use. So if we focus on this top left here, we start with 1,300 documents on the dot, but after we removed all of our 404 errors, we brought that down to 8,000. And once we've removed any documents that were too small, we were able to get around 5,600. And that story is pretty much the same for all the other collections. We started with a really large number, but unfortunately, just due to the nature of web scraping itself, a lot of those documents were just unusable, and a lot of the documents just didn't load for whatever reason. So now that I've gone over everything at a high level, let's go ahead and jump into the code for a more detailed analysis. So just as a reminder, all these notebooks I'm going to be using are going to be uploaded to GitHub. So if I'm going over to them a little too quickly, you're more than welcome to go into the GitHub under the scripts folder and just download them and look through them yourself. And all of these notebooks are being run on Google Lab itself, so I can make use of and take advantage of Google's resources themselves. So in terms of the updates, again, I just need to use PyMongo to connect to the database and write to it. And this is the code right here that I'm using to actually connect to the database. So certainly I've blocked out the actual IP address and my username and password for the server, but rest assured, what if you do put in the proper credentials, you're able to connect through them and then use the session variable to connect and access the different collections within sorry, not the PyMongo, but the MongoDB session itself. So this right here is one very succinct code block that I used to iterate over all the different collections so I can leave it run in the background and focus on some of the more pertinent issues in this project. So I have a list of all the collections I need to go through, and for each collection, I'm going to perform the cleaning on the document. So right here, I'm going to get all of the documents that aren't empty or don't match this really long regex right here. And all the different groups in this regex are basically the generic errors I was able to find through reading different website documentations and just the manual coding of the data set itself. So we have the biggest offenders here like 404, 403, but we also have some of the other ones like under maintenance, down for maintenance, can't find page, etc., etc. So once we query the database and get all the ones that don't match this regex or aren't empty, I'm going to create a new database called clean and just push them up to the database itself. And here are all the stats I was showing you before. Now with that out of the way, let's go ahead and go back to the presentation and continue onwards. So now that we've cleaned everything, let's focus on the actual sentiment analysis and tokenization of the data. So once again, we're going to be using PyMongo to connect to the database, but also we're going to need the help of pandas to perform the data analysis on and have like a very uniform way to structure our data and perform different operations on it. Now for the actual tokenizing and sentiment analysis, we're going to use GenSim and NLTK for different string preprocessing and tokenization functions. So let's focus on the tokenization first. Now, I know Nicholas already covered this a little bit, but on the actual HTML side of things, I'm given this really long string containing just the raw HTML itself. So as you can see here, there's going to be a bunch of new line characters that I need to clean, but also I need to remove all the stop words themselves. Now, in addition to the regular stop words, I'm also going to need to introduce some new stop words like different links or different symbols because those aren't really going to be meaningful when we want to tokenize them. So after I've performed the tokenization, transforming the big HTML file into a list of tokens that we can use, let's try and perform sentiment analysis on it. So for sentiment analysis, we're trying to predict and output a value between -1 and +1, where 1 is very positive and -1 is very negative. And by doing this, we can measure the impact and how each individual page was feeling about the project that we were querying for. So we can better get an idea of, okay, how is this project being received by the public itself? Now, to this end, I've decided to just use a pre-trained model in Python itself to perform the sentiment analysis. Now, in Python, there's a whole bunch of different pre-trained models that we can use, like Flare and Vader, but I ultimately settled for TextBlob due to its power and simplicity. So if we look at this next slide here, all I need to do is call the text blob library on a string or a set list of tokens, and it'll give me two numbers. It'll give me the polarity, which is the sentiment itself, from -1 to +1, but it'll also give me the subjectivity, which is unique to text blob. And the subjectivity is a measure of how subjective the model was in its analysis, where 0 is very objective and 1 is very subjective, open for interpretation. In order to actually apply this, I just need to do a lambda function and apply it uniformly across my data frame and store it inside the database itself. Now, once the sentiment analysis is done, let's talk about the topic modeling. Now, if you look at this slide, it's going to look very similar to Nicholas's because we use the same libraries to perform the same topic modeling on different subjects. So I'm going to use GenSim, NLTK, Pandas, PyMongo, and the PyLDAvis for the visualization. Now, like I said before, well, we already did the tokenization. So now that we have all the tokens, just like before, we just need to perform the data vectorization and feed it into the LDA model itself. Now, the biggest difference here is that all of the different documents in our collection and all of the different HTML files are going to be very heterogeneous. So, in contrast to performing topic modeling on the different abstracts and titles of the project itself, these different keywords are going to be very heterogeneous in terms of their size and diversity. So we can't just uniformly say, okay, for everything, let's just use 10 topics. So in order to alleviate this issue, I needed to do some hyperparameter optimization. So I needed to determine, okay, for this keyword, what is the best number of topics that I can use? Because if I use too many, then it's not going to have a lot of overlapping groups. But if I use too few, that may not be very insightful and it may be very heterogeneous inside the group itself. And in order to do this, I use a variation of grid search itself. Now, what parameter am I going to be optimizing based off of? So with LDA, there's going to be two main parameters. You have perplexity and coherence. So perplexity is a measure of, okay, I have this trained LDA model. I'm going to introduce a new document into it. How surprised or how perplexed, if you will, was the LDA model on receiving this new document? versus coherence, which is, okay, in one topic itself, how closely related are the different keywords there? And how well did it actually perform the topic modeling? Now, although I can perform the grid search on both of these, I decided to stick with coherence because it was more so what we were looking for this project. Okay, I have this keyword. I really want to optimize based off of how well each group in the keyword is structured. And once we perform this hyperparameter tuning to get the optimal number of topics that we need to use, we're going to then perform a visualization on them. So using the library that I was talking about before, we have this really powerful and interactive visualization here where we can click on the different topics that it generated and visually see, okay, I have this topic right here. Let me see all the keywords and how they relate to both the topic itself and the overall uh, distribution in all of the documents itself. But without that out of the way, let's go ahead and jump into the code itself and see how I'm doing this. So just like before, PyMongo, all of the different natural language processing libraries I'm going to need to use. And here I have the censored data like before. And here is where I'm performing the grid search CV. So for this analysis, I'm just checking topics 3 to 10. So I'm going to just train the model on all of the different choices I have for the topics and return the one that had the highest coherence. And here I have different functions which help me perform the different LDA and processing that I need to use. And here I have my automated script that I can run in the background. And you might even be able to notice that, hey, I'm actually running it right now as we get more data into the database. So I have the different collections here that I need to iterate over. And right now I'm just iterating over this one database. But for each collection that I need to iterate over, I'm basically going to query the database and get all of the unique keywords that we were able to generate in Nicholas's step. And for each keyword, I'm going to get all the documents for that keyword and perform the topic modeling and feed it through the pipeline so I can get all of the different topics for that keyword itself. And once I feed it through this entire code right here, I'm going to upload it back to the database. So now that we've performed all the analyses and gotten all the insights that we need to do, all that we need to do is just upload them and push them to the database itself, which we can use with PyMongo. Very nice and easy. So with that being said, that's going to be it for me. And I'll go ahead and pass you to the next person. Take care.
Howdy, my name is Benjamin Parrish, and my major contribution to this project was the administration and setup of our project database. In this section of the presentation, I will provide a brief technical description of the database, the factors that determined our setup, and the data we ended up storing on our database. The requirements of our project determined what solutions we chose for our database. The requirements of topic modeling required a flexible setup and the ability to efficiently handle large amounts of unstructured data. For these reasons, we opted for a NoSQL database. And of the options available to us, we unanimously decided on using MongoDB, as we were all familiar with it from the lectures we had in class. Now I will describe the machine we ended up using to host our database. Our original plan for hosting was to use ArcNet. We felt that this powerful system would provide the most benefit in terms of reliability and performance. However, we had to abandon this plan due to problems installing MongoDB on ArcNet. We were unable to install it as a package due to not being able to use any pre-existing package manager. We also had extensive issues that eventually proved to be insurmountable while trying to compile MongoDB from its source code. Eventually, we had to find an alternative solution, and the one we settled on was using an old Macintosh iMac 10. This was a relatively modest and older machine featuring Intel Core 2 Duo CPU, but it did have 16 gigabytes of memory, so overall its hardware specifications, while not ideal at all, were sufficient. I made the decision to install Debian 10 due to my overall familiarity with the operating system. Using a machine, using local hosting required some minor modifications to the local network on which the machine was hosted. These included opening SSH port 2222 to allow all members to interface remote into it, and the opening of port 27017, which is MongoDB's default remote port, and this was done to allow our website to directly interface with the database. Now I will explain our choice to use MongoDB. MongoDB, besides being presented in class, offered several advantages that influenced our decision to use it. The documentation for MongoDB is extensive and readily available on MongoDB's website. It proved to be relatively easy to install on the server and then configure it to accept remote connections. As I mentioned before, all team members were familiar with it due to having seen it demonstrated in our class lectures. The version of MongoDB we used was 4.4, which is not the most recent version. I believe the most recent version is in the version 6. But we had to use this due to the constraints of the hosting machine. More recent versions of MongoDB require instructions that our CPU just doesn't have support for due to its age, and thus we used 4.4. I will briefly describe how our data was organized and structured on our database. On our MongoDB instance, we had two databases which we store data on. The first one was called local, and it stored scraped HTML data that was the result, the output of our web scraper. And the second database was called tidy, and it stored data on the output of our project trace scripts. And in each database, we had our data categorized by the award which it was associated with. Now, on the local data, we just had scraped HTML data, but in our tidy database, we had cleaned HTML and our sentiment and subjectivity scores, and also a list of tokens that we used in that instance of the topic modeling script. Finally, I will discuss some problems we had in implementing and running our database, and I will expand upon some opportunities we could have to mitigate these issues and improve our database. The first subject I will go into is the issue of security. Our database is secured by a simple username and password combination that we assigned to each user. This is obviously far less secure than using SSH keys or authorized IP addresses to determine logins. Additionally, we do not have any access control implemented in the database itself. We didn't have, everyone can pretty much just go in and change whatever they want. Now, for a temporary database on a relatively small scale project, this is not a big deal, we feel, but if we were to have some kind of commercial service running based on this project, we would obviously want to harden our database significantly. The second issue is the problem of data redundancy. We don't have any replication being automatically performed. All our backups are done manually, and in the event of catastrophic server failure, which actually happened at some point during development, all the restoration had to be done manually, which caused extensive disruption and downtime. Implementing some form of automatic replication and rapid recovery would have circumvented this problem. However, for the hardware we ended up going with, this would be difficult to do, given that it's one single local machine. And then finally, there's the problem of the hardware we use. The Macintosh was a ad hoc solution when our first choice proved to be untenable. The computer itself is not an optimal machine for functioning as a server. It can overheat and needs to be restarted regularly to avoid crashes. Hosting on a cloud service would have outsourced this problem, but given the amount of hardware resources we needed, we did not find one that suited our needs. This concludes my portion of the presentation.
Alright, so I'm going to quickly demonstrate the Project Trace website. Right here we have a web app. This is it hosted locally, however we also have hosted it in the cloud right over here. I was able to accomplish this using Netlify. Netlify let me deploy the web app, which I created in Node.js over here in JavaScript. And as for the backend, I was able to host a Node server using Heroku. So if just hitting the Heroku backend, this is what it would look like right here. I was able to grab a bunch of elements, from the Mongo database. And so when you land on the home page, I have a short description of what Project Trace is. On the Visuals tab, let's see if we reload this. My bad. I've yet to push that, but let's see. Oh, there we go. Never mind. It should take a while to load. On the Visuals tab, we have some word clouds created for the data we collected on the government projects. I can add more in the future. And then on the separate tabs, we, for each of these things here, basically I pinged the Mongo database. Each collection right here is correlated to a government project, and from there I was able to grab all the keys and all the keywords, the related topics, the coherence of those topics, and the perplexity as well. In the future, I'm going to add as well the sentiment and the subjectivity. Here is what it looks like on the back end. I'm just pinging the server and displaying it on the front end. Going a little more into the back end right here, as you can see, in the for the Node.js file, I'm just getting the resources from the Heroku, from our Mongo database server right here, and then I create separate routes for each of them, and I just go through the entire collection. So for example, right here we have the DIBBSS award collection right here, and I just go through the whole thing and I gather all the objects and I send all the objects back as a giant JSON or a dictionary. And then for the web app, again, I create separate routes in the nav bar, and then for each element in the nav bar, I've created a component. For example, here's a component right here, and I go through and I fetch the data from the cloud-hosted node on Heroku, and then I'm able to display that over here in HTML with some style, which gives us what we see in the browser. And I believe that is all.